You're listening to DTFHN for February 22nd, 2026. I'm your architecturally unsound host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who build councils argue about scaffolding. Today's a day for staring at foundations and wondering who forgot the load-bearing walls. Let's get into it. A web page with no bottom, that's the detail that sticks. Not the algorithmic manipulation, not the data harvesting. The moment a page stopped having an end, your brain had learned over a decade of browsing that documents are finite objects. Then one day, they weren't. And something in the contract broke. Suzanne Paul wrote a piece this week drawing a clean line between social networks and what he calls attention media. The distinction is architectural, not cosmetic. A social network shows you what the people you chose to follow actually posted. Attention media shows you whatever keeps your eyes on the screen longest. Same interface, fundamentally different machine underneath. The timeline is worth tracing with some precision. Early Twitter, early Facebook. You followed people. You saw their posts in order. Notifications meant someone had actually interacted with you. Then, somewhere between 2012 and 2016, the platforms discovered that chronological feeds of your actual friends were insufficiently engaging. Engagement, of course, being a euphemism for addiction. The algorithmic feed replaced the chronological one. Notifications decoupled from meaning. Your attention became inventory to be sold. Run this forward. If the objective function is time on platform, every design decision optimizes for that. Infinite scroll removes the natural stopping point. Algorithmic feeds inject strangers because familiar voices are predictable, and predictable is boring. Notifications fire without cause because each tap is another impression served. None of these are bugs. They're the system working exactly as designed. The architecture dictates the outcome. Which is what makes Mastodon interesting. Not because it's better software, but because it's a different architecture. No algorithm deciding what you see. No engagement optimization. No advertising layer that needs your attention as raw material. You follow people. You see their posts. If nobody posted, there's nothing to see. That blankness, that silence is the feature. It means the system has no incentive to manufacture reasons for you to keep scrolling. The comments surface a sharp observation that even non-commercial networks should be careful about which patterns they replicate. Infinite scroll, quote, replies, like, counts. These aren't neutral design choices. They're attention capture mechanisms that function identically regardless of who runs the server. The protocol is open. ActivityPub federates. Anyone can run an instance. The off switch belongs to you. That's the structural difference that matters. Not whether the people running it are nicer, but whether the architecture permits you to leave. Moving on. Let me make the case against caring about any of this. Database transactions are a solved problem. They've been solved since the 1970s. A-side properties, write-ahead logs, isolation levels. This is textbook material, literally textbook. Every CS sophomore learns it. Why would anyone need another explainer? Because knowing the acronym and understanding the machinery are completely different things. And PlanetScale just published one of the most elegant demonstrations of that machinery I've seen. What makes this piece remarkable isn't the information, it's the craft. Interactive visualizations where you watch two sessions race against the same table. You see the moment session B's red returns stale data because session A hasn't committed yet. You watch a rollback erase changes that never existed from session B's perspective. The abstraction becomes tangible. You can feel the isolation levels working. Run this forward. Imagine every piece of infrastructure documentation built this way. Not static diagrams, not walls of text explaining what repeatable read means in theory. Beloove, animated sequences showing you exactly when row visibility changes, exactly how Postgres multi-versioning differs from MySQL's undo log approach. The technical depth here deserves attention. Postgres creates new row versions with transaction metadata, so each transaction sees its own consistent snapshot. MySQL overwrites rows in place, but maintains an undo log to reconstruct old versions on demand. Same guarantee, completely different engineering. That's the kind of detail that separates someone who can configure a database from someone who can debug one at 3 in the morning when writes are disappearing. The article's open, free to read. No paywall, no gated content. PlanetScale sells database hosting, but the knowledge sits there for anyone building anything. A student in Lagos learning Postgres isolation. A startup founder in São Paulo figuring out why their payment system has race conditions. The tools exist. The knowledge is available. And when it's presented with this level of care. With animations, you can slow down and replay, with side-by-side sessions showing exactly what happens and when. The barrier between understanding and not understanding just drops. One commenter asked what tool built those visualizations. That's the right question. Because the real craft here isn't explaining transactions. It's making the invisible visible. Turning an abstraction that runs trillions of times a day into something you can watch, pause, and genuinely understand. Making the invisible visible is one thing. Stripe's new Minions project is trying to make the invisible automatic. What happens when you build a coding agent on top of someone else's open source work, then keep yours closed? That's the question Stripe's new blog post accidentally answers. They've built something called Minions. One-shot coding agents that chew through their ticket backlog, generate pull requests, and hand them to humans for review. Thousands of PRs a week, they say. Built on a fork of an open source project. And the fork? Closed. The commenters noticed. Of course they did. Now look, Stripe is a serious engineering organization. They've contributed meaningfully to open source over the years. Ruby libraries, API design patterns, infrastructure tooling, real contributions. So this isn't a story about a villain. It's a story about a choice. And what that choice reveals about where the industry thinks the value is shifting. The technical substance here is thinner than you'd want. The post reads more like a recruiting pitch than an architecture document. One commenter called it a hiring ad, and that's generous. Hiring ads usually have more detail about the actual system. We get the broad strokes. Agent reads ticket. Agent writes code. Agent opens PR. Human reviews. But the interesting engineering question. How do you scope what an agent can touch? How do you handle the cases where the one-shot misses? What's the actual merge rate on these thousands of weekly PRs? Those answers aren't here. And that merge rate question is the one that matters. Because there's a version of this where AI-generated PRs genuinely accelerate development. And there's a version where they flood your review queue with plausible-looking code that takes longer to verify than it would to write. Anyone who's reviewed a junior engineer's PR knows the difference between code that works and code you'd trust in production. Multiply that review burden by thousands per week, and you start to wonder whether the productivity gain is real or just relocated. Moved from the person writing the code to the person reading it. The deeper irony is architectural. Stripe built this on open source foundations. The models, the frameworks, the fork itself. All of that exists because someone somewhere decided the blueprints should be public. And the system works. It works well enough that Stripe built an entire internal productivity layer on top of it. That's the open source thesis validated in real time. The tools exist. Anyone can build on them. But then the door closes behind you. That's not unusual. It's not even surprising anymore. It is, however, worth naming, because every time a company takes from the commons and keeps the derivative private, the implicit argument is that openness was good enough to get us here, but not good enough to go further. And that argument has a shelf life. The next team that builds this, the one that publishes their architecture, their failure modes, their actual merge rates, that's the team whose work compounds. Closed systems protect a position. Open systems build a future. Moving on. One commenter dropped a line that reframes this entire conversation. They said the jails versus containers debate misses the point. Docker won because of Docker files as executable documentation and a public registry, and they're right about Docker's success, but they're diagnosing a marketing victory and calling it a technical one. Consider cathedral architecture. Gothic cathedrals weren't built by inventing new stone. They were built by understanding load distribution so deeply that the walls could become windows. The flying buttress didn't add complexity. It revealed simplicity that was always possible once you understood where the forces actually go. FreeBSD jails are the flying buttress of process isolation. Linux containers are the scaffolding someone left up and then built a city on top of. The comments section has people who ran entire companies on FreeBSD in 2005 and loved it. Someone else asks a genuinely excellent question. Where's the technical write-up explaining how isolation actually works at a deep level? Not just the hand-wavy same kernel, weak isolation talking points. That question matters more than any of the advocacy because it reveals the gap. Most engineers choosing between jails and containers have never read the implementation. They're choosing ecosystems, not architecture. And the engineering underneath jails deserves real admiration. FreeBSD didn't need namespaces, groups, sec, comp, overlay file systems, container runtimes, orchestration layers, and a YAML specification to isolate a process tree. Jails landed in FreeBSD 4.0 in the year 2000, 25 years ago. One system called Geo. And you had a virtualized userland with its own root fileSend, network stack, and process space. The kernel knew what a jail was. It wasn't bolted on through 6 different subsystems that each solved one piece of the puzzle. Linux took the opposite path. As the article apparently frames it, Linux engineers built kernel primitives and then, in very Linux fashion, constructed an entire ecosystem of user space tooling to stitch them together. That's not a criticism. It's a design philosophy, but it's worth being honest about the trade-off. The Linux approach created a massive surface area for Docker and Kubernetes to colonize. The FreeBSD approach kept the abstraction in the kernel, where the kernel could reason about it as a single coherent thing. Someone going back to FreeBSD in 2025 isn't being nostalgic. They're making an architectural choice. The cathedral is still standing. The scaffolding city works too. It's just harder to find the load-bearing walls. We talked about finding what's hidden in complex systems. Volatility takes that literally, poise, pulling secrets straight from RAM. The version number is 3. That's the detail. Not 3.0, not 3.1, just 3. A complete rewrite, released in 2019, because after 10 years, the original codebase had accumulated enough technical debt that patching it was more expensive than starting over. Every engineer who's ever inherited a legacy system just felt a chill. Volatility does something most people never think about. It reads RAM, not files on a disk, not network logs, not the things a system is designed to remember. The things it's designed to forget. When you pull the plug on a machine, everything in volatile memory disappears. Volatility catches it before it's gone. Running processes, open network connections, encryption keys sitting naked in memory because the CPU needed them 3 milliseconds ago. The entire runtime state of a machine extracted and made legible. This is the tool forensic investigators reach for when they're analyzing malware, when they're reconstructing an intrusion, when they need to prove what was actually happening on a system at a specific moment in time. The example command in their documentation uses a file called stuxnet.bmem. That's not an accident. This framework cut its teeth on the kind of threats that make the news. Now here's the first principles question. Why does this need to exist as an independent framework? The answer reveals something about how operating systems actually work. Your OS doesn't give you a clean labeled map of its own memory. It can't. Memory is a living thing. Processes allocating, deallocating, sharing pages, mapping files. The kernel has its own view, but that view is optimized for running the system, not for explaining it to a human after the fact. Volatility has to reconstruct that explanation from raw bytes. And it has to do it for Windows, Linux, and Mac, each of which organizes memory completely differently. That's what the symbol tables are for. Hundreds of megabytes of structural definitions. So the framework can parse the specific kernel version that produced a given memory dump. The rewrite from version 2 to 3 came with a license change. They moved from GPL to a custom volatility software license. That's a choice worth noting without judgment. The Foundation clearly felt that the GPL wasn't serving the community the way they needed. The code is on GitHub. You can read every line. You can extend it, build plugins, contribute back. The extraction techniques are documented. The knowledge is available. Memory forensics is one of those fields where the gap between attacker and defender is measured in tooling. Every investigator who can pull encryption keys from a RAM dump. Every analyst who can reconstruct a malware infection timeline. That's capability that used to live behind six-figure consulting contracts. Volatility put it in a pip install. Completely different universe now. Story 6 takes us from software forensics to something wild, printing a language model directly onto silicon. When I first started working with transformer architectures, the thing that frustrated me most wasn't the math. It was the waiting. You'd watch a GPU burn through kilowatts of power just to shuffle numbers back and forth between compute and memory. The actual multiplication took nanoseconds. The fetch-store cycle took forever. I remember thinking, why are we treating a neural network like a program when it's really a circuit? Taalas asked the same question and then did something about it. They etched Llama 3.18b directly into silicon. The weights aren't data sitting in memory waiting to be fetched. They're transistors, physical gates. When your input arrives, it doesn't bounce between compute cores and VRAM 32 times. It flows through the chip like current through a wire. Layer 1 feeds layer 2, feeds layer 3, all the way down. No memory wall, no bandwidth bottleneck. Just physics doing what physics does best. The numbers are striking. 17,000 tokens per second. 10 times cheaper than GPU inference. 10 times less power. But let me play devil's advocate for a moment. A chip that runs exactly one model sounds like a terrible idea. Models update weekly. By the time you fabricate silicon, your architecture is 3 generations behind. Why would anyone want a read-only chip in a world that rewrites itself every Tuesday? Here's why that argument breaks down. Taalas designed a base chip with a generic transistor grid. Mapping a new model means customizing 2 mask layers, not redesigning from scratch. 2 months from model to silicon. That's slow by software standards, but the economics change the equation entirely. If your inference cost drops by an order of magnitude, you don't need the frontier model for every task. A hardwired 8 billion parameter model handling 90% of routine queries at a fraction of the energy. That's not a limitation, that's a deployment strategy. The comments hit on something important. Multiple people immediately saw the form factor implications. A model on a chip in a USB slot. Swap it like a cartridge. That's not cloud inference behind an API paywall with metered pricing. That's a physical object you own, running locally with no network overhead, no subscription, no kill switch. Taalas is building inference the way we should have been thinking about it from the start. The model isn't software running on general-purpose hardware. The model is the hardware. And hardware you hold in your hand is hardware nobody can take away from you. Moving on. In USMO of Dringan, a PM made a decision that reshaped computing forever. They unbundled software from hardware. Before that, you bought a machine and the programs came with it. Inseparable. After, software became its own discipline. The reason that matters now is that we're watching the same unbundling happen inside AI-assisted development. And most people haven't noticed. Boris Tain published his Claude Code workflow, and the core insight is deceptively simple. Never let the model write code until you've reviewed a written plan. Separate planning from execution. 2 distinct phases. 2 distinct artifacts. A human checkpoint between them. The question nobody in the AI coding discourse wants to sit with is this. Why does giving a language model more autonomy produce worse results? Every other tool in history gets better when you remove friction. Faster compilers, better debuggers, smoother deployment pipelines. The universal lesson has been get out of the way. But with language models writing code, the opposite is true. The more you constrain them, the more you force them to show their work before touching a file, the better the output gets. That's not a bug in the tooling. That's a fundamental property of how these systems fail. They don't fail at syntax. They fail at context. A function that ignores an existing caching layer. A migration that breaks ORM conventions. An endpoint that duplicates logic already living 3 directories away. The failure mode is implementations that work in isolation and shatter everything around them. Tain's research phase, where he demands the model read deeply, write findings to a persistent file, and submit that understanding for human review before any planning begins, directly targets this failure mode. The comments are revealing. Multiple experienced developers arrived at the same workflow independently. One called it Polya's problem-solving method, adapted for AI. Another pointed out Anthropic themselves recommend exactly this approach. The pattern is converging from multiple directions, because it maps to something real about how reliable work gets done, with or without a language model in the loop. What Tain documented isn't a Claude Code trick. It's a general principle about the relationship between understanding and execution. The plan file is an open artifact. You can read it, edit it, challenge it. The model's assumptions become visible before they calcify into code. That visibility is the entire mechanism. And it works precisely because it keeps a human in the loop, at the point where human judgment matters most, not at the syntax level, but at the architecture level. The tools exist. The workflow is public. Run this forward. Now for something entirely different. Story 8 takes us from code architecture to art history, pause, and the search tools that connect them. Don Rezabel Yu Giofi Guy, if that name sounds familiar, it should. He created jQuery, the JavaScript library that mass-democratized front-end web development in the mid-2000s. And then, apparently, he went and did the same thing for Japanese woodblock prints. The technical problem here is genuinely hard. Visual similarity search across art collections sounds straightforward until you realize what you're actually comparing. Ukiyo-e prints exist in multiple states. A single design by Hiroshige might appear in dozens of impressions across centuries, each with different wear patterns, color variations from different pigment batches, even deliberate modifications by different publishers. You're not matching pixels. You're matching artistic intent across a noisy, degraded, wildly heterogeneous corpus. Riz's approach pulls from multiple museum databases simultaneously: the Honolulu Museum of Art, the Museum of Fine Arts Boston, the British Museum, the Library of Congress, and others, each with their own cataloging systems, their own metadata standards, their own digitization quality. The search engine stitches these into a single queryable space. Upload a photo of a print hanging on your wall, on a postcard, in a book, and it finds visual matches across all of them. This echoes something from the early web that we've largely forgotten. In 1995, the Corbis collection started digitizing art, and Bill Gates personally acquired the rights to millions of images. The idea was that digital access to art would flow through a single commercial gateway. That vision lost. It lost because museums started putting their collections online directly. Because open standards made federation possible. Because the web's architecture favored distribution over centralization. Ukiyo-e.org is that architectural victory made concrete. One person building on Open Museum AP is, and open digitization efforts created something no single institution could. The prints themselves were mass media, produced in editions, sold cheaply, pinned to walls in Edo period homes. Democratized art, searchable through democratized technology. The site has been running since around 2012. Quietly, without a business model, without a paywall. The data is accessible. The tool works. That's the whole point. We talked earlier about tools built to last. Story 9 asks that question about language itself. How far back can you actually understand English? A PhD linguist wrote a fake travel blog about a fictional English coastal town. One post, one blogger, but every few paragraphs, the language ages by a century. By the time you hit 1200, you're staring at something that looks like German had a baby with Welsh. And the kicker is, it's all English, every word of it. Kalangori constructed passages stretching back 1,000 years, each one written in the style and vocabulary of its era. Modern English at the top, Middle English in the middle, Old English at the bottom. The whole thing reads like a controlled demolition of your reading comprehension. You're cruising through 1900. Victorian prose, a little stiff, but fine. Hound 17 nega, Hound 17 nega. Shakespeare territory, you can handle it. Then somewhere around 1300, the floor drops out. The letter thorn shows up. Yug, words you've never seen. Grammar that operates on rules your brain doesn't have installed. The comments are worth the trip. A Dutch speaker pointed out that Old English is actually easier for them to read than Modern English, which makes perfect sense when you remember that English and Dutch were practically the same language 12 centuries ago. We drifted. They didn't. Or at least not as far. Pull this thread and you land somewhere interesting. English is an open system. It has been for its entire history. It absorbed Norse. It absorbed Norman French. It grabbed Latin and Greek technical vocabulary wholesale. No academy controls it. No governing body standardizes it. French has the Académie Française. Spanish has the Real Academia Española. English has whatever people decided to do next. It's a language built by forking merge, not by commit. That's what makes this experiment work as more than a party trick. You're watching a language evolve without permission. Every century people just changed it, spelled things differently, dropped inflections, borrowed whatever they needed from whoever was nearby. The result is a language that 700 million people speak and that none of them can read in its original form. The tools exist to bridge that gap. Gory's whole project is making them accessible. No paywall on the core experiment. Just 1,000 years of linguistic drift, laid out where anyone can walk through it. We're rounding out today's lineup, and this last one might be my favorite. Let me make the case against this. Multiplayer games die for a reason. The player base leaves. The servers cost money. The developer moves on to the next thing. Trying to revive them is nostalgia cosplaying as community organizing. You'll get 12 people in a lobby for one evening. Everyone will say that was fun. And then nobody will come back next Tuesday. That's the argument. And it falls apart the moment you look at what actually kills multiplayer games. It's almost never that the game is bad. It's a coordination problem. You want to play, I want to play. But neither of us will launch the client unless we know the other one is already there. Classic prisoner's dilemma. Everyone defects to whatever has the biggest active player base, and the smaller games starve. The game didn't fail, the matchmaking economy failed. Gamedate is solving exactly that problem. It's a scheduling layer. You register interest in a game, you pick a time, other people see that commitment, and suddenly the coordination problem dissolves. You're not hoping someone else is online, you're making a date. The comments mention deadlock showing up on the site, which technically isn't even released yet. That's actually perfect. It means the tool works for any game where the core issue is finding people, not finding servers. What I admire about the execution is the restraint. This isn't trying to reverse engineer server infrastructure or rebuild netcode. It's not a technical solution to a technical problem. It's a social solution to a social problem. The game already works. The people already exist. They just need a meeting point. And the whole thing is beautifully simple. That old-school Steam UI the commoners love isn't just aesthetic nostalgia. It's a signal. This is for people who remember when multiplayer meant something you organized, not something an algorithm served you. This has been your daily tech feed for Hacker News for February 22nd, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go make something worth sharing. We'll see you back here tomorrow.